Alright everybody, if you made it this far into the videos, you know we are now on the section talking about differentiation. We've done integration, so we're going to numerically differentiate. And in order to do this, as you can tell, or what we might have not talked about, the integration was actually pretty much using trapezoidal rule style area under the curve calculations. It was just doing it and automatically finding the best way to find the area under the curve to fill it in and give the integral between bounds. For our purposes, for differentiation, it's important to note that MATLAB isn't an analytical solution, it's a numerical solution. And as you can imagine, trying to find a numerical version of differentiation is going to be kind of challenging. What we can do is make the horrible assumption that dy dx is approximately the same thing as saying delta y divided by delta x, right? So we're going to take the difference between y and x and kind of equal those two. And the nice thing is there's a couple of equations that exist, or functions that exist in MATLAB, that let us do this, that make this process very easy for this. And that is the function of diff and gradient. Now I'm going to start with diff because it's a little bit simpler to wrap your head around, but then from then on out, it's gradient will probably be a little bit more powerful to use. Now what the difference function does is it actually just, if you have a sequence of variables, let's say it's 1 to, let's say we have a vector of 1, 2, 4, 6, 8, 10. So we have those values. Now if I did diff of x, what it's going to do is it's going to find the difference between 2 and 1, 1, and then 4 minus 2 is 2, 6 minus 4 is 2, 8 minus 6 is 2, and 10 minus 8 is 2. So it's just the difference between each value between x. Now you can see it does matter. It's not an absolute value, so if I said negative here, you'll see that it does, it's the second position minus the first position, so it's going to be 2 minus 1 is 1. Sorry, 2 minus 1 is 1. Negative 4 minus 2, that doesn't work. Why does my head hurt? Oh, sorry. I didn't do the difference. I gotta do that. Diff of x. There you go. That makes more sense. Okay. It's getting late. 2 minus 1 is 1. Negative 4 minus 2 is negative 6. Good, that makes sense. 6 minus a negative 4 is 10. Negative 8. So you can see it is in that order. So that works really well for us. So if you can imagine, if we're going to find a function and we want to know the derivative of, then we would just have to have some x vector equal to something. We'll fill in something in a little while. We'll have y equal to a function of x, and then to find our dy dx is simply going to equal to diff of y dot divided by diff of x. And that's it. And that's how how we can do this. So let's try this out. So now let's make x something. Alright. X, you are now something. Let's make this and let's make this, oh, I don't know, 0 to 8, to 0 to 0.8, and we'll do this in 0.1. Then we'll do a spacing of 0.1 from 0 to 0.8, and we'll say y is a specific function. So in this case, we'll say 0.2 plus 25 times point star of x. Now I'm actually taking the exact equation that we use in my notes so that you can follow along on your own, but 675 plus 675 dot times x dot to the fourth, and make sure I have all these dots because dots are super important. I don't need a dot there. Well, I have lots of extra dots there. Let's get rid of that. Okay. Good. To the fourth plus 400 dot times x dot to the fifth. Alright, that sounds good. So that's our y's. And so now we're going to differentiate that with just that. So let's CLC, clear, run this, and we have values for our column, our y value, dy dx value, and so now the question is, did this actually work? So now to check to see if this actually worked, we have to look at a couple of things. First and foremost, let's look at our variables. One thing you'll notice, it doesn't quite show this here, but we can do this by, I'll do the length command. If I showed you the length of x, you'll see it's 9 positions long. If I did the length of dy dx, it's 8 positions long. Why? Because it's actually the difference between each row column, so it's subtracting them, so it has to be just one less. So if I wanted to plot, say, x versus y, these differences are actually going to be in between the x value. So like this is the derivative that sits between 0 and 0.1. So I'm going to have to go through all the positions of each one of these values and find that midpoint value of x so that I can plot dy dx versus x if to look at this. So we can do this. I'm going to do this by saying first know the length of the vector of x, so we have 9, and then I'm going to redefine a new set of x plots is equal to x of m, and this is going to be x, and so here we're going to have to play with indices again. We're going to go 1 from n minus 1. So what this does is it goes to everything up into the length minus 1, so it's the first 8 values, plus x from 2 to the n, and the second 8 values, and taking all of that, and I'm going to dot divide it by 2. And that'll give me a new value. Now just to show you really quickly what I was actually doing x, it's taking this value all the way up to this vector and then adding it with all of these. So it's effectively adding these two values, these two values, these two values, these two values, and dividing by 2. So it's finding the average point between each one, which is as it should. So that works. So now I can plot, in this case, x or xm versus our dy dx, and we get a plot that looks like that. That doesn't. Oh, well, okay. That doesn't quite look right from what I would think. So I gotta pause this. All right, I'm gonna leave this in because it's kind of funny. I copied and transposed my equation wrong, but we're gonna leave it because we're gonna check to see if this works on this one. This isn't actually the same equation in the figure, but we can play with it and let's see if this works. So I really want to compare if what we got here, this plot for this set, and it shows you as a line. I'm going to actually convert this into data points because I would prefer to see it as such. There you go. Now I want to compare that to what the actual difference, because we can analytically differentiate this. So I can say y prime, the actual differentiation is going to equal to, well, this is derivative of 0 is plus 25 times x minus 200 dot times 2 dot times x plus 675 dot times 4 dot times x dot to the third plus 400 dot times 5 dot times x dot to the fourth. Okay, so if that is correct, I can say this that. There you go. And now I am going to, nope, too much. I am going to hold the plot, and I'm going to say plot x to the y prime, comma, what was it, comma? Let's plot red. And what do we see here? Hopefully it's, oh great, it works. So you can see this is the derivative of the one that fits the other. Let me correct my silly mistake earlier to match the figure, because the equation is a little bit more interesting than this. It looks like I missed the minus, it's 675 dot to the third minus 900 dot times x dot to the fourth. So it's a slightly more interesting equation. We can copy that, and actually I will go ahead and redo I will redo this one here, and so it's 675 dot times 3 dot to the squared minus 900 dot times 4 times 4 dot times x to the third plus 400 dot times. Okay, and so there we go. So I think that's it. So let's copy and paste all this again. Let's rerun that. Okay, I'm going to release the plot. Release the plot. And let's redo the prime. And there you go. The prime looks a little bit more interesting. And we can replot. Let's hold. Go back to our previous plot. Not prime, but dm dx. And we get a pretty good fit. So that's, in a nutshell, how you can do this. Now, one of the things I'm going to point out is that's a pretty rough estimation. One of the things I should mention is our derivative through this approach gets better and gets more improved if we go to smaller step sizes of x. As x step size gets smaller, these terms tend to get a little bit better. So if I go here and plot that in, and now I'll have to redo our xm equation. Oh, first I have to redo our length, because we have a new length. N is equal to length, and xm is equal to that. And so if I replot that, and I'm going to actually overlay it. Let's see how that looks. It's going to look weird, but that's fine. And you can see here, the previous one was a little bit more jagged and less smooth. With a new one, and with the derivative that we said, it smooths out a lot better. The values get a little bit more interesting, and you can start to see what's actually happening here, and they get a little bit more accurate. So that is, in a nutshell, numerical differentiation, numerical differentiation in MATLAB. Now, the one thing I did mention earlier is you could do the same thing through the gradient method, the gradient function. The difference with the gradient function is, and I'll show it over here on the slide, it actually evaluates the difference at the beginning and end, but all middle points, you no longer get a midpoint difference on it. You're actually going to get a value difference on each independent point. It's actually going to be the gradient with the forward gradient minus the back gradient divided by 2. So it actually gives you the gradient, or the change that happens at each value of the vector based upon the before and after numbers. So it's a little bit more accurate, and the real nice thing about it is this part right here, that you don't have to no longer do this funky conversion of x sub n, where you have a smaller vector size now because you took the difference. The vector size will remain the same. So if I was to redo what we were doing here, all I could say is gradient y and gradient x, and let's hide that, okay. Copy and paste all this, enter, and importantly over here, our dy dx, x and y all have the same dimensions, so I no longer have to find or redefine a new x series. I can just plot x versus dy dx and get, do I still have it on hold? I've been keeping it hold. Let me close it. Plot, and I can just keep it as such without any longer worrying about the values there. Now, just for sake, let's plot y. This is the actual y versus x, and if I was to hold that and plot your dy dx on that, and let's make it red this time, you can see what the derivative looks like versus the actual raw plot that there is. And that is finding differentiation numerically in MATLAB. And so hopefully that'll be good for now. I'm going to continue this on Sunday with the rehashing of a redemonstration of the what do I say, the ODE solutions, and we'll go from there to find the rest. But I think this covers the entirety of the numerical integration, numerical differentiation, finding optimization, and finding zeros. That's a lot of things to find. So hopefully you'll have a great weekend, and I'll see you on Tuesday.